Hi, my name is Martin Kuliš and I'm a junior professor at the Department of Software Engineering at Charles University in Prague.
Hello, I'm Mirek Kotopil. I'm a PhD candidate at the same department.
And together we would like to present to you a paper called Detailed Analysis and Optimization of CUDA K-means algorithm. Although there are many papers on the subject, we have found that none of them provide detailed analysis of the individual steps. Furthermore, it is very hard to find a decent open-source implementation of CUDA K-means. That is why we have decided to go once more under the bridge and to perform our own detailed analysis and our own implementation. So let's begin. At the very beginning, I would like to give you a quick refresher about the K-means algorithm. Let's have some data represented in vector space. The main objective is to group this data together, since data which are located close by are likely to have similar properties. The algorithm works with a model which comprises a set of centroids, aka means, and this model is updated iteratively. In each iteration, the algorithm performs two steps. First, it computes an assignment for every data point, which means it basically computes an Euclidean distance between every point and every mean, every centroid, and then it finds nearest mean for each data point. The update step computes a new version of the model where each mean is computed as a center of mass of its corresponding cluster. The assignment part of the algorithm is somewhat similar to matrix multiplication. We basically need to compute a dot product between every vector from means with every vector from data points. Unlike the matrix multiplication, the results of this dot products does not have to be kept in the memory all the time, but right after these dot products are computed, we can use the minimum reduction to compute the assignments. This similarity is rather important since the matrix multiplication has been studied thoroughly and we can draw inspiration from the documented optimizations. However, this transformation is not straightforward since we need to adapt the algorithm for the subsequent reduction. The algorithm may be optimized in several ways. The first optimization was already suggested in previous slide. We can fuse the computation of Euclidean distance and the means-wide reduction into one step. Another possible optimization is to compute the sum of coordinates inside the assignment step. Although this optimization does not reduce the amount of work, it actually can improve the data flow since each data point needs to be loaded only once. On the other hand, some of these optimizations may raise additional issues in parallel processing. For instance, the last mentioned optimization will enforce data synchronization in case the points are processed concurrently. Hence, our objective is to investigate all these optimizations and all possible approaches to parallelization so we can re-implement K-means more efficiently.
Why would we implement K-means again? We have actually found that there was no implementation of K-means fast enough for the use cases we have here. I'm going to talk about the use cases now.
In particular, I believe this picture sums up our situation pretty well. The dataset growth is nowadays omnipresent, which is also the case of, for example, cytometry, which is our main motivation. Cytometers produce measurements of millions of data points in a sample. The measurements usually have less than 50 dimensions, which makes them pretty easy to process with K-means. On the other hand, you only have several seconds for the analysis because the analysis usually needs to be interactive. For example, the dataset here can get processed by K-means to reasonable clusters which are much easier to work with. More complicated use cases arise in multimedia processing. For example, we have participated in VBS competition multimedia modeling conference where the participants are required to find a particular video frame in a huge collection of videos. The videos, as annotated by neural networks, have thousands of dimensions, millions of data points, and for the clustering that would help you to organize the videos into something meaningful, you usually have less than 1 second. Another use case in multimedia is the real-time segmentation of video, which might get very useful, for example, in artificial intelligence because it can prepare your pictures from the camera to a simplified form which is probably easier to ingest for the neural networks. The task might seem simpler because you get pictures with less than 10 dimensions, On the other hand, the whole computation needs to get finished very quickly. You only have 50 milliseconds between two frames in 20 FPS, so your implementation needs to be really fast. The new result that we are describing in this talk is the new implementation of K-means that we have produced, which is sufficiently fast to work with all these use cases. As you can see in the table, the implementation can reach speeds of hundreds iterations per second, which makes it easily applicable to many more interesting use cases.
Now let me tell you how we did it. First we analyzed individual steps of K-means algorithm, then we integrated the results into the complete solution. I would like to start with a few important facts about modern GPUs which heavily influenced our design. First of all, a GPU comprises a few thousand cores. If these cores were to process different data, they would require memory throughput in the order of tens of terabytes per second. Unfortunately, even stacked HBM2 memory is about 2 orders of magnitude slower. Therefore, clever caching plays a significant role in performance optimizations. Second, the cores are not completely independent, but they execute code in lockstep. In lockstep, adjacent cores are issued the same instruction in one clock cycle. Therefore, it is better to use algorithms that do not rely on heavy branching, which might lead to code divergence. Let's start with the assignment step, where we utilize the idea of clever caching. Our approach is inspired by a caching technique known in matrix multiplication as tiling. Data of matrices are divided into tiles, which are cooperatively loaded by thread blocks in shared memory. Therefore, data needed by all threads in a block does not have to be loaded from the global memory repeatedly. If one thread computes more than one dot product, it can use this technique again to cache values in its own registers. Hence, every value loaded into a register participates in several multiplications. The tricky part is to select the right size and shape of the tiles on each level so they would fit available resources. Furthermore, this technique has to be adapted for Euclidean distance, and we also need to perform the reduction that finds the nearest mean for each point without storing the distances back in the global memory. We have tried several approaches, and here I would like to present the best two of them. First one is denoted Rex caching strategy, because in this strategy we use registers to cache the input data as well as the intermediate results. It is very similar to tiling approach. We cache fragments of input matrices in shared memory and smaller fragments in registers. We also cache intermediate dot products in the registers, which are later aggregated into intermediate minima. The second approach, which is called fixed caching strategy, is more different. It manually caches only means in the shared memory, while data points are left to hardware L1 cache. The shared memory window has fixed size, so it does not comprise all dimensions. And finally, the registers are used only to cache intermediate results, not the input data. It is rather difficult to find the right size and shape of caching windows, as well as the appropriate workload division among the threads. Furthermore, the best strategy also depends on the input parameters such as k or the number of dimensions. We have answered these questions empirically. After the assignment step, we need to compute a new set of means. For each data point, we need to add its values per dimension to the corresponding vector in the new means matrix. The challenging part is how to allocate threads for this job. Naive approach would allocate one thread for each mean vector, which iterates over data points and their assignments. Although this approach requires no data synchronization, it provides limited opportunities for parallelism and bad data flow. Better approach is to allocate a thread per data point, so each thread adds one point vector to its corresponding mean vector. The updates require synchronization, which may be achieved by atomic instructions. We can improve previous approach further by allocating one thread per input value. This way, adjacent threads will work on different dimensions, which will reduce the amount of atomic update collisions. Empirical analysis revealed that the atomic updates are almost as fast as normal write operations if the collisions are rare. A collision occurs when multiple threads attempt to update the same value in the matrix. Hence, the best performance is achieved if the means matrix has at least as many items as there are GPU cores, assuming the updates are distributed uniformly. If the matrix is small, we can improve the odds by privatization. The matrix is copied multiple times in the global memory, and the collisions may be reduced by assigning different copies to different thread blocks. The cost we pay for privatization is the subsequent reduction, which aggregates all copies into the final means matrix. Therefore, we need to choose the amount of copies carefully, since too many of them may create a bottleneck at the end of the update step. Another possibility is to place private copies in shared memory. However, shared memory of a thread block is valid only while that block is running. Therefore, the copy in the shared memory has to be added to a matrix in the global memory before the thread block is terminated. To fully utilize benefits of shared memory privatization, each thread has to process more than one value, so every thread block iterates over a larger portion of data points. Finally, we constructed several complete k-means implementations, which can be divided in two categories. The first category is called composed solutions, since it's merely composed from the individual kernels from the previous steps. The first kernel handles the assignment step and produces assignment vector, which is kept in the global memory. The second kernel takes the assignments and computes a new version of means matrix, which is used as the input for the subsequent iteration. The greatest benefit of this approach is that we can select the best algorithms for both steps individually, based on the configuration of the problem. In the second type of implementations, we fuse the kernels of both steps together. The benefit is that we do not need to pass assignments from one kernel to another via global memory. Furthermore, with clever caching, the data points need to be loaded only once, both for the assignment and the update step. On the other hand, fused kernels have to reach certain compromise in thread distribution and resource allocation, especially in case of the shared memory. In this video, we have tried to focus on the main ideas. However, there are many technical details which are also fairly important. We invite you to read about them in our paper.
Finally, let's have a look at how fast we can actually get.
The paper contains lots of benchmarks and measurements and experiments that were used to ensure and validate that the computations we do are optimal and the results are the best we could get. Most of the computations are measured in normalized time, not in real time. Normalized time is used for comparing the different overheads of the algorithms independently from the actual size of the problem. Let's first have a look at the assignment step of k-means clustering. We have compared and benchmarked three main approaches to the caching of the data in the assignment step. We have compared baseline, which doesn't do any explicit caching, with fixed and rex caching strategy. Notably, the baseline approach scales nicely and provides pretty good performance, especially if the number of dimensions is low, but it is easily overperformed by the other caching strategies. For example, the registers caching strategy has outperformed the baseline several tens of times, especially on lower dimensions and higher counts of clusters, because this is benefited by storing of the data in the shared memory. On the other hand, if the dimensionality of the problem gets higher and number of clusters gets lower, the registers caching strategy will have problems from not having enough possibilities to parallelize. Also, the shared memory cache will kind of start running out and the performance is going to degrade. The fixed caching strategy actually seems to scale a bit better than the registers caching strategy, especially for higher dimensionalities. On the other hand, for the lower dimensionalities, higher cluster counts, which are important subclasses of the problem parameterizations, especially for the meta-clustering, the registers caching strategy may be 2 or 3 times faster. So we are using the registers caching strategy for this parameterization for the rest of the paper. The update step of the algorithm is most complicated by the necessity of writing too much data into too small space in the memory of the graphics card, which is most slowed down by the write conflicts that can happen. From all the approaches to reduce the overhead of writing so much data into so small memory in the least possible amount of time, the best strategies we have found were those using atomic instructions to locklessly write and increment the numbers in the memory. From the simple strategies that we have tested, atomic find was actually the best one. Atomic find strategy works by parallelizing over all available data over n data points and d dimensions and adding the numbers into the W matrix one by one. This can be sped up further by not immediately executing all the atomic write instructions at the time when the data is loaded, but by processing several points of data in succession and coalescing the writes into one big write using some kind of cache. We have called the resulting approach atomic shared memory. It works very easily. It just aggregates several consecutive atomic write instructions into the shared memory that's available for the thread and writes all those into the main memory at once. Notably, this results in 2 times speed up over the normal writing strategy, which is great. On the other hand, if the number of clusters is high, the shared memory strategy actually starts requiring too much shared memory, and also the probability of saving a conflict decreases, so the efficiency of the shared memory strategy decreases as well, up to the point where it is probably just as fast as the atomic find update strategy. Another way of reducing the number of write conflicts during the update step is basically making several private copies of the whole output data of the W matrix and using different copies of the matrix by different threads, which reduces the probability of the conflict. This is especially helpful for low numbers of clusters. For example, at 16 clusters, the amount of write conflicts can reduce the performance of the computation by a factor of 3 or 4, which can get solved just by making 4 privatized copies of the data. On the other hand, for larger numbers of clusters, the performance is actually pretty good even without private copies of the data. And moreover, adding more copies of the data can start thrashing the level 2 cache and lead to performance decrease in extreme cases. The main outcome of this is that the optimal number of private copies of the data differs significantly for different parameterization of the problem. On the other hand, we can assume that having 8 private copies is pretty good choice for all problem parameterizations on current hardware. In the paper we have compared several final versions of the algorithms. The best one was the best combination of the low-level primitives optimizations for specific parameterization of the problem that we could obtain. We have also tried 2 fused versions of the algorithm where the assignment kernel doesn't produce the assignment vector into the memory but is immediately feeding the output into the update kernel, which can also lead to interesting speed up. We have compared those against the baseline, which is the primitive not optimized algorithm that we have started with. And we have also compared to CUDA, which is one of the not many open source implementation of GPU k-means. Most interestingly, we have found that despite CUDA uses a complicated indexing and filtering scheme called yin-yang, which it uses to remove a significant part of the computation from each iteration of the k-means, it doesn't help it a lot to compete against even the baseline implementation that we had. In particular, in most problem parameterization that we have tried, it was actually outperformed by the factor of 10 to 100. Moreover, the baseline algorithm was outperformed by the optimized versions of the algorithm on all parameterizations of the problems that we have measured by a factor of at least 5. The performance of the final versions of the algorithm allows you to process the data or run the k-means iterations really quickly. For example, for 256 clusters on 8 dimensions, you can run around 1000 iterations per second for 1 million points. For a more complicated dataset of 128 dimensions and 4000 clusters, you can actually run at least 5 iterations per second on a dataset of 1 million points. We believe that the achieved performance can open doors to many new applications of k-means algorithm, especially with the new high-dimensional, very large datasets.
In conclusion, we've got an implementation of k-means which is significantly faster than the existing ones.
The implementation is available on my GitHub. So thank you for your attention. We hope you enjoyed this video and we are looking forward to your questions.